Tēnā koe. This video is the follow-up to the polymerization video, and this one is all about how we can hydrolyze condensation polymers. Please note that addition polymers cannot be hydrolyzed. This first slide reminds you of a few of the natural and synthetic polymers that exist in your world today. Hydrolysis is the chemical opposite to condensation. In condensation, we were joining molecules by removing a small molecule. And in hydrolysis, we are splitting a large molecule by adding in water. Hydro meaning water and lysis meaning splitting. So to hydrolyze something, you need water, an acid or base catalyst, and you need to have heat or, even better, reflux. Let's check out the hydrolysis of polyamides. Drawn is a typical polyamide, and the first thing we need to do is identify the amide functional group and draw a line down the center of it as shown here. This is where the amide gets split by the water being added in, and it gets split into its two original monomers. One is a dicarboxylic acid and the other is a diamine. If it's split in acid hydrolysis, we still get two monomers. It still splits in the same place, and one is still a dicarboxylic acid and one a diamine. However, in acid hydrolysis, all functional groups that can be are fully protonated. The NH2 groups are in NH3 plus forms, and the COOHs have that H, that proton added. While in base hydrolysis, everything is deprotonated as it is in basic conditions. So the COOH groups actually have the proton missing, COO minus, and the NH2 groups do not have that extra proton that they did for acid hydrolysis. Taking a look now at the hydrolysis of polyesters, having a look at a typical polyester here, again we need to find the functional group, which this time is an ester. We need to draw a line down the center of it to show where it splits, and again, whether we hydrolyze it in base or acid, it will separate to two monomers. This time we have a dicarboxylic acid and a diol if we've hydrolyzed it in base, and also if we've hydrolyzed it in acid, we also get two monomers, a dicarboxylic acid and a diol. Again, we have to look at the differences between acidic and basic hydrolysis. In acidic conditions, the dicarboxylic acid is fully protonated. However, alcohols are unable to lose that proton, so it's always going to form an alcohol. As we see the base over here, the carboxylic acid has lost its proton and it's got a sodium ion. The alcohol is still an alcohol. So for ester hydrolysis, we always make an alcohol, and we either make a carboxylic acid or the salt of a carboxylic acid. Something that's important to note is that in hydrolysis, we can never form an acyl chloride, even if the acid used for the catalyst is hydrochloric acid. This is because if you remember back to your organic chemistry, acyl chlorides react violently with water. And so if we're sitting in water, as we would be with hydrolysis, we're never going to form an acyl chloride. So you can use acyl chloride to start to build your polymer, but it will never be the product of hydrolysis. We're going to spend a fair bit of time now looking at fats and oils, which are special polyesters. Remember, these are a molecule of glycerol joined to three fatty acids. And you can see here a couple of ways you can make these. Tristerin in the center has three of the same fatty acids joined to the glycerol. And you can see on the right a different kind of fat which has three different fatty acids joined to the glycerol molecule. Let's take a look now at how saturation affects fats and oils. Taking a look at the general structure of a fat or oil, it becomes apparent that these fatty acid chains could have carbon-to-carbon multiple bonds, making the fat or oil unsaturated as well. Whether fats and oils contain saturated or unsaturated fatty acid has a bearing on how good they are for human health. Fats or oils containing saturated or trans-unsaturated fatty acids have a more linear shape, and as we know from bonding, things with a more linear shape can pack closer together and thus have a higher melting and boiling point. A higher melting or boiling point means that these fats can form plaques or can block your arteries a lot easier than fats with lower melting points, and this can lead to heart disease. So many people choose plant oils or polyunsaturated fats as a better health alternative, and now you know why. The last thing we're going to look at is the hydrolysis of fats and oils. Firstly, in acid conditions. Taking a triester, adding water and acid catalyst with reflux. Firstly, as usual, we need to find the functional groups. There are 3 functional groups in a triester, and we're going to cleave that right down the middle. It's going to then split to make glycerol with 3 alcohol groups. As remember, alcohol groups cannot lose their protons. And then it's going to reform 3 fatty acids. And as it's an acid hydrolysis, the fatty acids will have their protons, will all be protonated. Let's now have a look at the base hydrolysis of fats and oils, which is slightly different. Again, we need reflux to make sure this reaction happens. We need to find the 3 ester groups in the fat, and we need to draw a line down the middle of them to show where we're going to break them apart. As usual, we form glycerol because alcohol groups cannot lose their protons. But this time, because it's in base conditions, instead of the fatty acids having their protons, they have all lost that proton. And they could have a metal cation forming an ionic bond with the O-. You can draw the product of base hydrolysis either way, with or without the metal cation. But note that the salt of a fatty acid is actually known as soap. Yes, this is how you get the soap that you wash your hands with. That brings us to the end of this video on the hydrolysis of polymers. It can look a bit tricky, and it does need a little bit of practice, but keep using your patterns and remember that a lot of it's just copying. See you later.